Now we will introduce a new cycle. It's called a regeneration cycle. It has a higher efficiency even than reheat cycle. Okay, so how does the regeneration cycle work? First of all, we still have a boiler. That's where the water gains heat. We call the exit number 1. And then 1 to 2 still the same as before. You will go through a steam turbine. The mass flow rate here is m dot 1. Okay, so now all of the superheated water vapor will go through only part of the turbine. For example, here we call number 2, 1 to 2, going through part of the turbine. And then at number 2, what will happen is you separate the fluid into 2 streams. Okay, so let's do that. The first stream will just directly leave the turbine. Leave the turbine. And the rest, let's use color blue for the rest. The rest will go through the rest of the turbine. Will go through the rest of the turbine. And then it comes out of the turbine. We call it number 3. And then number 3 will go through a condenser. To further cool down. So 3 to 4. Condenser. And then we pump up the pressure. 4 to 5 is a pump. 4 to 5 is a pump. And then what's going to happen is number 5 will go to a tank. And number 2 will also go to a tank. Let's draw this tank. Okay. So you can see the hot water, number 2 in red, will go to this tank. The cold water in blue, number 5, will also go to this tank. You can think of this tank just like the sink in the kitchen. Hot water goes to the sink. Cold water also goes into the sink. And then they mix up. They mix up. Okay, the mass flow rate for the first stream, let's call it m dot 2. And the mass flow rate for the rest, we will call it m dot 3. So hot water has a mass flow rate of m dot 2. Cold water has a mass flow rate of m dot 3. They go to the sink, they mix up. So what comes out of it? First of all, what comes out of it has to be the total mass flow rate, which is m dot 1. So we use color black. We call this number 6. Hot water number 2 goes in. Cold water number 5 goes in. They mix up. So what comes out of it is number 6, which is warm water. Okay, and then before we send number 6 back to the boiler, we need to send it up to a pump to pump up the pressure. Pump the pressure. So 6 to 7 is the pump. And then send number 7 to the boiler to gain heat. And this sink where hot water mixes up with the cold water has a name. This sink is called open feed water heater. Okay, and then what is the relation between the 3 mass flow rate? The total mass flow rate is m dot 1, and it's equal to the combination of the other two, m dot 2 plus m dot 3. m dot 2 plus m dot 3 is equal to the total mass flow rate, and it's color coded. Okay, so this is how a regeneration cycle works. All of the fluid 1 to 2 only goes through part of the turbine, and then you separate the working fluid into two streams. One of them, number 2, will just directly come out of the turbine, indicated in red color. The rest will continue to go through the rest of the turbine, 2 to 3, indicated in blue color. And then they meet up again in the open feed water heater. Number 6, which is the warm water, comes out of the open feed water heater. And then you send number 6 to a pump before you send it back to the boiler. Okay, so now next step is to sketch the whole thing on a T versus S diagram. T versus S diagram. So first of all, let's draw a vapor dome. And now let's sketch a constant pressure line. This is the pressure in the boiler. Let's start from number 1. Number 1 is the exit of the boiler. Exit of the boiler. It's usually superheated. Superheated. Okay, let's sketch 1 to 2 first. First of all, we should use color black because 1 to 2 has a mass flow rate of m dot 1. 1 to 2, steam turbine. How do we sketch 1 to 2? If it is steam turbine, it's always isentropic. If it is isentropic, it should always go straight down. So 1 to 2, go straight down, color black. And to make look pretty, we can add one more constant pressure line across number 2. So 1 to 2 goes straight down, and the mass flow rate is m dot 1, so it should be color black. And then 2 to 3, how do we sketch 2 to 3? 2 to 3 is still going through the turbine, so it is still an isentropic process. So 2 to 3 should still go straight down. But this time, the mass flow rate has changed to m dot 3, so we change the color to blue. And then we sketch 2 to 3, continue going down vertically. 2 to 3. This is my number 3. And then to make things look nice, we can add one more constant pressure line for number 3. Okay, now let's sketch 3 to 4. 3 to 4 is the condenser. That's where you lose heat. So if you lose heat, you also lose entropy. So x coordinate becomes smaller. You have to go to the left. 3 to 4, go to the left. And you always cool down to F point. So 3 to 4 to the left. And then 4 to 5. 4 to 5 is the pump. You pump up the pressure. Back to which pressure? You pump up the pressure to the same pressure as number 2. So 4 to 5, isentropic compression, we go straight up. Up to where? Up to the line that has the same pressure as number 2. So 4 to 5, that's where number 5 is. Go straight up, and it should be on the same constant pressure line as number 2 is on, because the pressure of number 2 will be equal to the pressure of number 5. Okay, so now let's sketch 5 to 6 and 2 to 6. Let's start from 5 to 6. 5 is cold, and cold water goes in while hot water number 2 also goes in. They mix up, so warm water comes out. So for 5 to 6, it's cold going in, warm water comes out. It's actually a process to gain heat. So how do we sketch 5 to 6? 5 to 6 is a process to gain heat. If you gain heat, you also gain entropy. So entropy must become bigger. The x coordinate becomes bigger. If the x coordinate becomes bigger, you should move to the right. And in this open feed water heater, it's a constant pressure process. So 5 to 6 should be along this constant pressure line and to the right. So 5 to 6 should along this constant pressure line and to the right. Okay, and then what about 2 to 6? What about 2 to 6? Number 2 is still very hot. Hot water goes into the open feed water heater, while cold water also goes in. What comes out of it is warm water. So for 226 is hot water going in and warm water coming out. It's a heat loss process. How do we sketch a heat loss process for 226? If it is a heat loss process, you also lose entropy. If you lose entropy, you must move to the left because entropy is the x coordinate. And again, this is a constant pressure process, so 226 must be along the constant pressure line and to the left. So you can see 226 going to the left, while 526 is going to the right, and they will have to meet up at somewhere. Where do they meet? They usually meet at the F point. Blue meets red at F point. And that is my number 6. We use color black for number 6 because the mass for it becomes m dot 1 again. Okay, and then 6 to 7. How do we sketch 6 to 7? 6 to 7 is a pump, so we pump up the pressure. It's isentropic compression again, so we go straight up. 6 to 7 goes straight up. And then 7 to 1, just a boiler. That's it. Okay, so that is the diagram. The black one has a mass flow rate of m dot 1. If it is black, that means the mass flow rate is m dot 1. If it is red, that means the mass flow rate is m dot 2. And if it is blue, the mass flow rate is m dot 3. And again, the relation between them is total mass flow rate m dot 1 is equal to m dot 2 plus m dot 3. This is how you sketch the whole process on a T versus S diagram. Okay, so now we do some mathematical analysis. Why do we prefer this cycle? Why does this cycle give us a high efficiency? Let's take a look. So first of all, because we have so many mass flow rates, we're going to introduce a new parameter that is called y. What is y? It's defined as m dot 2 over m dot 1. We define this ratio as y. So what will be m dot 3 over, let's write it this way. So what will be m dot 3 over m dot 1? First of all, we can rewrite m dot 3. M dot 3 can be rewritten to m dot 1 minus m dot 2 over m dot 1. So this equation becomes 1 minus m dot 2 over m dot 1. And we know we just defined m dot 2 over m dot 1 as y. So this equation becomes 1 minus y. And then what we do is to have left-hand side divided by left-hand side. It must be equal to right-hand side divided by right-hand side. Okay, left-hand side m dot 2 over m dot 1 divided by m dot 3 over m dot 1. It must be equal to right-hand side divided by right-hand side. And now you can see we can cancel m dot 1. So what is left is m dot 2 over m dot 3 is y over 1 minus y. Keep that in mind. Okay, and next one. Like we said before, 226, hot water goes in, warm water comes out. It's a heat loss process. 526, cold water goes in, warm water comes out. It is a heat gain process. So there must be an equation for them. The heat loss for process 226 must be equal to the heat gain for process 526. We know heat loss for process 226 must be equal to the heat gain process 526. And do you remember how to find heat transfer? Yes, from first law. What was the format? Q over M, Q dot over M dot equal to what? The difference of the two enthalpies. And we always use the higher enthalpy minus the smaller enthalpy. So from here, we can write heat transfer must be equal to M dot times H high minus H low. So now let's apply this format back into this equation. So Q dot 226 must be equal to Q dot 526. Let's rewrite each Q dot. 226, first of all, what is the mass flow rate for 226? 226 is red, so mass flow rate is m dot 2. Multiplied by the difference of the two enthalpies. Which one is higher, 2 or 6? Which one has more energy? Number 2 is hot water going in. Number 6 is warm water coming out. Number 2 must be higher. H2 minus H6 equal to right-hand side. What is the mass flow rate for 5 to 6? 5 to 6 is blue, so that's mass flow rate m dot 3. Multiplied by the difference of the two enthalpies. Which one is higher, 5 or 6? If you take a look, 5 is cold water going in, 6 is warm water comes out. So number 6 must be higher. So we use H6 minus H5. And from here, we can rewrite this equation to m dot 2 over m dot 3 equal to H6 minus H5 divided by H2 minus H6. And don't forget, we just defined m dot 2 over m dot 3. So we can continue to rewrite m dot 2 over m dot 3. Continue to rewrite m dot 2 over m dot 3 with y over 1 minus y. And from here, we can solve for y. What is y? You just perform the algebra. The solution for y is h6 minus h5 divided by h2 minus h5. So what do you notice? Even if y is a new parameter that we just introduced in this example, it is still a function of the enthalpies. So still, if you solve for a question for regeneration cycle, the key is still to look for enthalpy of every single point. Even y can be found from all the enthalpies. Okay, so now let's start from the first one. First one, let's look for how much work can be generated from this cycle. Generating work that's in the turbine. Okay, so let's recall what was the format for work. The format is always W dot over M dot equal to the difference of the two enthalpies. This comes from first law. And we always use the higher enthalpy minus the lower enthalpy. So from this format, work can always be rewritten to mass flow rate times the difference of the two enthalpies. Okay, so now let's use this format to look for W dot T. Work generated by the turbine. So actually we have two steps for the turbine. The first one is 1 to 2. The second step is 2 to 3. So now let's apply this format. What is the mass flow rate for process 1 to 2? 1 to 2 is black, so the mass flow rate is m dot 1 multiplied by the difference of the two enthalpies. Which one is higher, which one is lower? 1 is higher or 2 is higher? 1 to 2 is the steam turbine. That's where you lose heat. So 1 must have more energy. So we use H1 minus H2 plus the second term. What is the mass flow rate for 2 to 3? 2 to 3 is blue, so the mass flow rate is m dot 3 multiplied by the difference of the two enthalpies. Which one is higher, 2 or 3? 2 is the inlet, 3 is the outlet. 2 to 3 is the turbine, that's where you lose heat. So number 2 must have more energy. H2 minus H3. Okay, And then usually we prefer to write this equation into such a format: W dot turbine over M dot 1, which is total mass flow rate. So we divide every term by M dot 1. Right hand side becomes H1 minus H2 plus M dot 3 over M dot 1. What is M dot 3 over M dot 1? Let's take a look. M dot 3 over M dot 1 right here has a name. What is it? It's 1 minus y. So here it becomes 1 minus y. Then multiply by H2 minus H3. So now take a look at the right hand side. What is right hand side? Right hand side is just all the enthalpies, even if y is not in the format of enthalpies at this moment. But what is y? Take a look here. Y is also a function of enthalpies. So essentially, everything in the right hand side is just a function of enthalpies. Okay, so this is how much work can be generated. Next one, how much work will be consumed? W dot pump. Okay, so here we have to take a look because we have two pumps. The first pump is 4 to 5, and the second pump is 6 to 7. W dot 4 to 5 plus the second pump 6 to 7. And now let's rewrite each one of them. What is the mass flow rate of 4 to 5? 4 to 5 is in color blue, so the mass flow rate is m dot 3. Multiplied by which one minus which one? 4 to 5 is the pump. That's where you add electricity or energy into the system. So you must have more energy at the end. So number 5 must be higher. Same thing. 6 to 7, what is the mass flow rate? 6 to 7 is color black. So the mass flow rate should be m dot 1. Multiplied by which one minus which? 6 to 7 is the pump. Again, that's where you add electricity, add energy into the system. So you must have more energy at the end. So you should use H7 minus H6. Okay, so now again, the format that we usually use is W dot pump over M dot 1. So we divide every term by M dot 1. Okay, first one, M dot 3 over M dot 1. Do you remember what is that? So okay, if you don't, let's go back. M dot 3 over M dot 1 right here again is 1 minus y. 1 minus y times H5 minus H4. And then plus H7 minus H6. That's it. And right hand side again is just a function of enthalpies. Okay, and then number 3, what is the net amount of work that the system can generate? W dot cycle over M dot 1, that is equal to W dot turbine, work generated, minus W dot P, work consumed, divided by M dot 1. So this equation becomes M dot W dot T over M dot 1 minus W dot P over M dot 1, and we derive the equation for each one of them. So we just combine them together. The solution is H1 minus H2 plus 1 minus y times H2 minus H3 minus 1 minus y, H5 minus H4, and then minus H7 minus H6. So this is the net amount of work that can be produced from this regeneration cycle. Okay, and then part 4, how much heat do you have to provide? Q dot hot. Okay, and there's only one boiler, that is process 721, and it's color black, so the mass flow rate is m dot 1. M dot 1 multiplied by, okay, enthalpy, which one minus which one? Because 7 to 1, 1 is the end. The end must have more energy. So H1 minus H7. So solution is H1 minus H7. Okay, and then part 5. Part 5 very similarly is Q dot cold. Cold is the condenser. Where is the condenser? Condenser is in color blue. That's 324. So the mass flow rate is m dot 3. M dot 3. Okay, which one minus H, which one? 324 is condenser. That's where you lose heat. So you must have more energy in the beginning. And the beginning is number 3. So H3 minus H4. And from here, we can find Q dot C again over M dot 1. And again, what is M dot 3 over M dot 1? It's 1 minus 1 times H3 minus H4. Heat gain, heat loss, and then finally efficiency. How do you look for efficiency? Efficiency is equal to W dot cycle, what you get, divided by what you pay. What do we pay? Q dot H. And then we divide both of term by mass flow rate M dot 1. M dot 1. So now, do we have the expression for both of them? W dot cycle over M dot 1 comes from part 3. Q dot H over M dot 1 comes from part 4. So you just combine them together. That's it. So now, as you can see, again, if you want to solve for a regeneration cycle problem, what is the key? The key is just look for enthalpy of every single point. And Y can also be found from enthalpies right here. As soon as you find enthalpy of every single point, the problem is solved. So that is the analysis we have done about regeneration cycle.